In this video, I'd like to look at how we can use a very simple physical model for a particle in a gas phase to understand something about what temperature really means. So what I'd like to do is propose that we've got some sort of box. Now I've cut away the front face and the top face of this box so that we can look into it. And I'm going to put a particle in here, and I'm going to further suggest that this particle moves only in the x direction, at least for now, and we'll add more directions later. So as this particle is moving, it's going to move not only to the right but also to the left. It's going to bounce back and forth between the two walls on either side, and it's going to have a total momentum of its mass m times its velocity, which I'll call v sub x. All right, so this is how we can characterize, if you will, the physics of this particular particle. Now, what we're going to be interested in is determining what force this particle exerts on the wall of the box. So ultimately, we're going to convert this into a pressure. But for now, let's just focus on how to calculate the force. Well, from basic physics, we know that force is equal to the mass times the acceleration in the direction that it's moving. Now, acceleration, in turn, can be thought of as a change in time of the velocity. So as the velocity is changing with time, that results in acceleration. Now, in this particular simple model, rather than using derivatives, I'm just going to treat this as though it is a small change in velocity that accompanies a small change in time. So we can think of this force as being written as mass times delta Vx over delta t. Now, since the mass is constant, I can bring that in. It doesn't change, so the delta of mvx is simply m times delta Vx, so those are both the same. But it's really telling us now that force is related to a change in momentum with respect to a small increment of time. Now, when we get to the wall, I want to be able to calculate what the change in momentum is. At the wall, if it has an elastic collision, we're going to have a momentum of mvx going to negative mvx. In other words, the net change in the momentum is simply going to be twice the momentum, twice mvx. Now, what do we do about the change in time? What time increment is involved here? Well, we're going to propose that it relates to the time between successive collisions with the wall, so the amount of time between those collisions. So we've got to have to calculate this basically based on the distance that the particle travels divided by its velocity. Well, what is that distance? Well, the distance is going to be how long it takes to hit the wall and then go all the way to the other wall and back again. So we're going to say that the length of the particle in the x direction, the length of the box in the x direction, is L sub x. So the total distance is going to be twice that, or 2L sub x, and the velocity is still v sub x. So we have a ready-made way of calculating what delta t might be based on these considerations. So now if I put all this together to try and get to the force, the distance, the change in momentum is simply 2 mvx, and the change in time is simply the distance divided by the velocity. Well, I can now cancel out the two factors of 2, and I can move the v sub x to the top, and my net result is going to be my force is the mass times the velocity squared divided by the length of the box. Now, we're going to go a little bit step further and say the particle, there may be many particles moving in this direction, and they're going to have a variety of different velocities. So we're going to substitute an average velocity squared for the velocity squared. All right, it's a small change, but you'll see in just a moment why this is important. Now I want to go to a new screen. I've got the picture reproduced up there again, and I've got our final result for the average force. But now what I want to do is consider what happens if I have a whole bunch of particles. This is one gas particle. If I have a total of n particles, I want to use that force that those n particles exert on the wall to evaluate a pressure. I'll remind you that pressure is simply the force divided by the area. But what area are we using in this case? Well, the area is the area of the box, that is the wall of the box that these particles are hitting. If they're all moving in the x direction, that area, for example, would be something like a, y, z, where y and z are the two coordinates that are perpendicular to x. So we're assuming, if you will, a rectangular box in this case. So now when I use my expression for the force, and I use the area, and I multiply this by n particles, I'm going to end up with an expression that looks something like this. I've got the n particles in front, I've got the average force per particle in the x direction in parentheses, and then I'm dividing by the area that it's hitting, the area of that wall. And so this is going to represent, if you will, my mechanical pressure. Now, I'll notice that here, the length of the box in the x direction times the area of the box in the y and z directions is simply the volume of the box. So rather than deal with particular dimensions here, I'm simply going to substitute the volume in there so that I can rewrite this pressure as simply the number of particles times this average velocity squared times mass divided by the volume. All right, now a question that arises now is, what if we want this particle to move in many directions? It doesn't have to just move in the x direction. Is there a way that we can include that? Well, to do that, I want to consider 3D isotropic motion. Now, what does that mean? That means isotropic means that it's got the same characteristics in all three directions. So the Vx direction is no different from the Vy direction or the Vz direction. So if I write my total velocity squared, it's going to be the sums of the squares of these three components. So v squared is equal to vx squared plus vy squared plus vz squared. Now, this is for any instance of velocities. If I'm interested in average velocities, the average velocity squared would simply be the sum of the averages of those square velocities. But now here's where we're going to bring in this isotropic quality. If it's isotropic, this means that these three components, v sub x squared, v sub y squared, and v sub z squared, are no different from one another. They're all the same. So that means we can rewrite the total velocity squared as simply be 3 times vx squared, because vy squared, vz squared are just the same as that average value. So now we have a way of using this to substitute the total velocity squared for v sub x squared in our expression for the pressure. So now when I write my pressure, instead of writing Vx squared, I'm going to write it as V squared over 3. So now my pressure is the total number of particles times the mass times the velocity squared, the average value, divided by 3 times volume. All right, we're almost to the end. What I'm going to need to do now, though, is consider how this compares to other things we know about a gas. Well, the average kinetic energy of a gas particle is 1/2 mv squared, so that would be just one particle. If I have a mole of gas particles, I would need to multiply this by Avogadro's number. And since this is the average kinetic energy, I can consider this to be the average kinetic energy of a mole of gas particles. And I'll write that as E sub kin in these angle brackets. So that's the average molar kinetic energy. Now, the number of particles is always going to be equal to the number of moles times Avogadro's number. Avogadro's number is just the number of particles that are in 1 mole, so the number of moles times that would give me the total number of particles. So if I substitute this in, if I multiply my average kinetic energy by some number of particles n, that's just going to be equal to the number of moles times Avogadro's number times that average kinetic energy, which means that it's equal to the number of moles times the average molar kinetic energy. So I end up getting that my number of particles times the average kinetic energy per particle is just the number of moles times the average molar kinetic energy. So now I can begin to substitute this in for the things in my expression for pressure, which I've reproduced here. Notice that I have the number of particles times mv squared. Well, that's just twice the average kinetic energy. So I can rewrite this as 2n times the average molar kinetic energy divided by 3v. Now, how do I deal with this? Do I see some things that are familiar? I'll remind you that the ideal gas law says that PV is equal to nRT, where n is the number of moles. All right, so now if I take this into account, I can move the volume in the expression for pressure over to the left side to get an expression for P times V. And when I substitute that in here, what I'll end up with is that nRT is equal to 2/3 times the number of moles times the average molar kinetic energy. And I can rearrange this equation now a little bit, multiply both sides by 3/2, and what I'll end up with is that the kinetic energy, average molar kinetic energy, is 3/2 times R times temperature. Notice I've canceled the number of moles on both sides because it appears on both sides of the equation before that. Now, this is a special equation, and it's telling me something very important. Remember that the gas constant is a constant. The only things that can vary here are the temperature on the right-hand side and the average molar kinetic energy on the left-hand side. So this is telling us that there is a direct relationship between the two. And what it means is that when temperature is higher, the average molar kinetic energy of the particles is greater. In other words, they are moving faster. Their mass isn't changing, they're moving faster. When temperature is colder, then the average kinetic energy is getting less. Now, this leads us to an absolute temperature scale, so that when temperature goes to 0, it essentially means that the particles are not moving at all. So that is why the Kelvin scale is so important for us, because its 0 is absolute 0, which corresponds to a system in which there is no more residual motion. All motion has ceased and everything is at a complete standstill. So this is our reason for defining temperature this way. I want you to begin thinking of temperature intuitively as being related to the motion of particles. And when temperature goes to 0, particles stop moving.